This video we're going to cover angle of twist. This is a slightly more complex problem, so if you don't understand the basics of angle of twist, it might be good to review those. Okay, determine the absolute maximum shear stress in A36 steel shaft with diameter of 60 millimeters, which is fixed at both ends. So keep in mind that we're fixed at both ends even though you can't see it. So what do we know? We're given the diameter. I automatically make that into a radius in meters, and we know A36 steel, so we can determine constants like G or E. So we also know tau max is TC over J. We know angle of twist, TL over JG, and we know J. So here we're looking for tau max, but we can't really find tau max because we have unknowns TA and TB. So those are the first things that we need to find. So basically, because we have two unknowns, we know we're going to need to find two equations with two unknowns so that we can end up eliminating or substituting. So the first thing that I do is write the sum of the torques about the shaft, and I create this convention where anything in the direction of TB and TA is positive in this case for the overall shaft. So TA plus TB minus 500 minus 200 equals 0. So I end up with my first equation, TA plus TB equals 700. From there, what else do we know? We know that the ends of the shaft are fixed. So the overall angle of twist from point A to point B is going to be equal to 0. And we also know that the sum of the angle of twist of each section is equal to the total angle of twist. So we can say that 0 equals angle of twist AC plus CD plus DB. So we're going to have three chunks. And then I wrote out the equations fully. And I can pull out a 1 over JG because that will be constant. Okay, so this is very important. Whenever we're going to start off with this section AC. So I cut the section and I look at everything to the right of the cut. So when I cut it, I have my TA, and when I cut it, remember that the surface from where you cut, everything outward from that direction is in the positive X. So if you point your thumb outward and you curl your fingers, the positive convention is going to be this way. So we know that we need another torque going the opposite direction of TA down here to counterbalance this TA here. So TAC, the torque for this section, is going to be positive TA. Okay, I hope that kind of makes sense. So then we cut between CD and look at everything to the left. So this way. So we have a TA, we have the 500 from TC, and we have to determine what this unknown is here. So once again, everything that points to the positive X, that's where your thumb is going to point, and you curl your fingers so you know that this direction is positive. That's what our sign convention is. So what we can say is this unknown is going to be TA minus TC, and it's going to be positive. So we know that for section TCD, we have TA minus TC, so it's TA minus 500. And then for the last section, I cut here, and I choose to look at everything to the right. So I have a TB going this way, and that means I need something to balance it out, so I'm going to have another TB going this way. But in this case, when I curl my fingers, so I point my thumb outward in the positive X direction, when I curl my fingers, the positive convention is actually this way, so this is going to be negative TB. So now I have determined all of my internal torques for each section for AC, CD, and DB. And that's the most difficult part to get right just because of the sign convention and understanding where you're cutting. So from there on, here are the things that we just found. And what do we know? We determined our equation for angle of twist. Now if I use this equation, I can multiply JG over to this side, and because it's 0, JG doesn't matter. So we're left with this equation. So I plug in all of my lengths. and all of my T's. So TAC is TA, 1 meter, TCD is TA minus 500 at 1.5 meters, and TDB is negative TB at 1 meter. So then I just distribute everything out, and I end up with a final equation of TB in terms of TA. And I also, remember, have another equation that we determined in the very beginning where we have these two unknowns. So now I can use these two equations. So start with this TB, plug it into this first equation, and now I have an equation with just TA in there. So do your algebra, and you end up with TA equals 414.29 newtons. So then you can take this TA, plug it back into the equation, and you end up with TB is 285.71 newtons. So now we've got our TA, we've got our TB. What do we have to do? Remember, we have to determine the absolute maximum shear stress. Now, to determine the absolute max shear stress, we have to determine the internal torques at every section. So now we know what TA and TB are. So we said that TAC is positive TA, TCD is TA minus 500, and TDB is negative TB. So we know what those are. So now that we found the internal torques for all three sections, we look at the maximum torque, which happens to be TAC with 414.29, and then we can solve for the polar moment of inertia. And remember, C is always the outermost radius. So in this case, we have a solid shaft, so it's going to be the 0.03 meters. And then we just plug into our tau max equation, where T is going to be T max of 414.29. C is the 0.03 meter radius. Plug in the J, and I end up with 9.78 megapascals for maximum shear stress. So this is a very good problem. The most difficult things I would say is the sign convention, knowing where to cut and finding like the internal torque for every section. From there on, once you have your unknowns, it's just plugging in and doing algebra. So I hope that helps a little bit.